This is my Physics 2 Lab 3. The purpose of this lab is to measure the distance dependence of the magnetic field due to a small bar magnet and compare your measurements to the distance dependence predicted by the equations for the on and off axis magnetic fields derived from the PHYS law. This will be done using tools such as a digital compass app and GlowScript. How similar are findings in the experimental model and the computer model is the question we'll be asking. The only formula we apply in this lab is the Biot-Savart law shown below, as well as related formulas to make it easier to do the math. The formula calculates the magnetic field strength at a given location. In this lab, we assume that objects in the surroundings, except for Earth, have a negligible effect on the magnetic field produced. For Earth, we account for the field generated by lining up our experiment from magnetic east to west. In this lab, the system is the bar magnet, while the surroundings is everything else in the universe, including Earth, objects nearby, and excess magnetic fields from other sources, which we hope are negligible. The initial conditions for this lab are basically just finding the magnetometer on the phone using a given procedure. We use this location along the axis of the bar magnet during the experiment, and this way we can ignore the z-axis of the magnetometer readings, which should be fairly consistent over the course of our procedure. The preview of our results is shown below. The data we collected from our experimental procedure is shown here from a screenshot of our Excel file. On the right side, the graph of the natural log of the strength of the field in the x direction versus the natural log of our radius for each of those locations shown here, as well as the formula for its best fit line. This best fit line will be used in calculations on the next slide to figure out mu. The calculations shown convert the equation for the best fit line on the graph on the previous page in order to find both our slope, which is shown using n at negative 3.0835, and mu, which ended up being 2.075 units. The formula on the bottom for mu was derived using the Biot-Savart law formula. The first half of the code is shown on this slide with the mu magnitude that we calculated from our experiment shown on the left as mu mag, which equals 2.075 as discussed before, as well as the function for calculating a magnetic field of a dipole, which is what our bar magnet simulated. To get the best results possible for our visual model from the GlowScript code, I used a B-scale of 1000 and a distance of 0.2 meters throughout. This slide shows the second half of our GlowScript code, with each little section applying the function we defined before for the magnetic field strength of a dipole at various locations, as well as doing it at an intermediate angle as defined by ops underscore 45 degrees. The results of this model are shown here, with the theoretical off-axis field turning out to be 2.614 times 10 to the negative fifth teslas. There was a 60.565% difference in our results for the magnet strength between experimental and computer models. The Biot-Savart law and distance dependence can be applied to the bar magnets with fairly accurate results. The bar magnets can be used to model magnetic dipoles, with distance being the most important factor to figuring out this strength. Some potential sources of error that were included in this lab was the non-exact measurements via the meter stick, slight issues with aligning the magnetometer east and west, and failure to account for outside noise such as computers and cellular devices nearby. The magnetometer accuracy for the app Teslameter on iOS may not have been perfectly exact as well. What if we hadn't oriented the experiment to compensate for magnetic north? The x and y coordinates would have been affected by the magnitude of the magnetic field of Earth at this location, ruining the data as the field is fairly strong in comparison to the bar magnet. In our experiment, we accounted for this by subtracting from the y value only, but if we did it from some intermediate angle, we would have had to adjust for Earth's magnetic field in all three directions. And what if we were to stick two identical our magnets together, it would basically create a dipole with double the strength, and therefore our magnetic field strength would increase by about a factor of 2 at all locations.